Hello everybody and welcome. This is To The Point Learning, and this is the fifth video in a 10-part series covering everything we need to know for the AQA 9-1 GCSE Chemistry course. And in this video we're going to be going over the topic of energy changes. So let's get started. So the first thing before we really go into anything in this lesson is we need to be familiar with this principle, conservation of energy. And I'm sure you guys have heard it in your previous lower school lessons. And that is that energy can never be created or destroyed, only transferred. Okay? And the same is true for chemical reactions. Energy can only be transferred. So energy is conserved in all chemical reactions. And therefore, since chemical reactions we do observe temperature, so change of energy is occurring, there must be a transfer of energy between the reactants, the reagents, and the surroundings. And whether the net energy transfer is going into the reactants or to the surroundings, well, there's two different types of reactions. And that follows that we can have an exothermic reaction. So that's a reaction in which energy is transferred from the reactants to the surroundings. So we observe a rise in temperature of the surroundings. And we can also have an endothermic reaction, which is the opposite. It's where energy is transferred from the surroundings to the reactant. So it's absorbed, energy is absorbed into the reagents. So therefore we observe a decrease in temperature of the surroundings. So let's have a little bit more of a look at exothermic reactions. So we know here that an exothermic reaction will result in a rise in temperature of the surroundings because energy is being transferred from the reactants to the surroundings. So let's have a look at a few examples. So one of the most obvious examples will be combustion. And the combustion of fuel, combustion of wood, combustion of anything. And this is very exothermic because since it releases a lot of energy. Another example would be many oxidation reactions. So here we have the reaction of sodium with water to produce sodium hydroxide and hydrogen. And we know from our previous lessons that the sodium is an alkali metal and it's very reactive. So it reacts quite vigorously with water and produces a lot of heat and other forms of energy as well. Another example is all neutralization reactions. So acid plus an alkali, which neutralize to make water, that is also an exothermic reaction. So take a note of these. Just try to remember these three examples because they are quoted in the specification. So practical applications of these exothermic reactions include self-heating cans, hand warmers, so things you put in your gloves to keep your hands warm if you're going skiing or something, and a combustion engine, so everything in cars that make cars move. We've got exothermic reactions, which chemical reaction produces heat, which is then captured and used and converted into kinetic energy. So now let's look at the opposite, so endothermic reactions, which is a transfer of energy from the surroundings to the reagents. So what we observe is a decrease in temperature, a reduction in temperature of the surroundings. So let's have a look at a few examples. So one of the reactions that we do need to know, and this is quoted in your specification, is that of citric acid and sodium hydrogen carbonate. Bit of a mouthful there. And this is an endothermic reaction. But one of the other ones that is more obvious is thermal decomposition. So where you heat something to break it down. So a good example of this is heating of calcium carbonate to produce calcium oxide and carbon dioxide. And here I've included that reaction there. And you do need to be familiar with this. But this is quite obviously an endothermic reaction because calcium carbonate is not going to break down into its constituents without a bit of prompting, without a bit of energy from the surroundings. So that makes sense that it's an endothermic reaction. So it absorbs energy from the surroundings in order to carry out. And practical applications of these is a good one to quote in your exam is sports injuries pack. So if you get an injury and the medical team come over and they put a cool pack on you, and this is an endothermic reaction going on because it's instant cool without the need of a freezer. But really what we need for all of these reactions is we just need an awareness, of the change in temperature. But we also need an ability to construct an evaluation when given necessary information about the applications that is referring to. So you may be given a quote in your exam covering something about a sports injury pack, and you'll be given some information, and you just need to depict with the information that they give you and collate it into a nice evaluation. You don't need to know too much about it. They will give you all the information you need to know. So don't be worried if you get across something, get given an example that you haven't come across. That's all okay. You just have to look into the question. So the next section is bond energies. We've looked at whether a chemical reaction is overall exothermic or endothermic. But if we look at a chemical reaction, and every chemical reaction for that matter, two things must happen for a chemical reaction to occur. Firstly, bonds between the reactant molecules have to be broken. And this process of bonds being broken is endothermic. It requires heat from the surroundings, for example, in heating. But then once the bonds between the reactants have been broken, the product molecules must then be formed. And this involves bonds being formed. And bonds being formed is an exothermic process. It gives out heat. Now note that both of these processes occur regardless of whether it's an exothermic reaction overall or an endothermic reaction overall. Every chemical reaction involves these two processes, okay? And whether a reaction is determined as exo or endothermic, well, we're going to get onto that now. So let's have a look here. So this is an exothermic reaction. And as we said before, there's two processes. There is bond breaking and bond formation. Now, for an exothermic reaction, the energy used to break the bonds in the reactant molecules must be less than the energy produced, so less than the energy produced when the bonds between the product molecules are formed, which gives out heat, an exothermic process. So if this side of the reaction produces more heat, and this is giving out heat, produces more energy rather, well then the overall reaction is going to be exothermic. Now let's look at the opposite. So for an endothermic reaction, so the overall net energy change is to the reactant molecules. Well, therefore, that must mean that the energy required, energy used in bond breaking, so the energy taken in from the surroundings, is greater than the energy produced when the bonds between the products are formed. So there is an overall net change in energy from the surroundings to the reactant molecules. So the reaction is endothermic. Okay? Make sure you understand this. This is important. So the next section is bond energy calculation. So using what we've just understood, we need to quantify that. We need to put it into numbers. So every chemical bond has a specific bond energy that has been calculated from experiments done by the scientists. And this is how they will be given to you in the exam. So this thing here shows this shows that our chlorine bond has a bond energy of 242 kilojoules per mole, and it will always be in this format. Now, a good way to really understand how to do these calculations is just to go through a question. So that's what we're going to do. So using bond energies below, calculate the energy change for the reaction. Okay? So this is the reaction here. We've got hydrogen reacting with chlorine for produce hydrogen chloride. Okay? That's all we need to know. But we also need to know that what the bonds are going on in here. Okay? So we've got two hydrogens reacting together here to form one hydrogen bond, and two chlorines reacted together to form one chlorine bond. And then also here we need to note that we've got two molecules of hydrogen chloride. So therefore we've got two here. And we need to know that, and we'll see why in a minute. Now the bond energies for these are here. So we've got a chlorine bond, which has that bond energy, hydrogen bond with its corresponding bond energy, and then a hydrogen chloride bond. So in order for this chemical reaction to work, well, the first bit we need to work out is the energy required for bond breaking. Well, the bonds that are broken initially are here. We have a hydrogen bond being broken, one hydrogen bond, because there's one bond between two molecules and there's only two molecules of hydrogen in there. So what we have, and the same for the chlorine. So what we've done is we've just taken the bond energy for hydrogen here and added that to the bond energy of chlorine. So we get an overall bond breaking energy requirement of 678 kilojoules per mole. But the next process is what is the energy when the bonds are formed. So when here the product molecules are formed. And well, there's two sides to here. We've got two molecules of hydrogen chloride. So we need to calculate the hydrogen chloride bond and multiply it by 2 to get its bond formation energy. So this is what we've done here, okay? 2 multiplied by 431 kilojoules per mole, which gives us a bond formation energy of 862 kilojoules per mole. Now remember, bond breaking, so this process requires heat. It's an endothermic process. And this process here, bond formation, is an exothermic process. Gives out heat. So to calculate the overall change, we have to take the bond breaking energy and subtract the bond formation energy. So we do 678 kilojoules per mole minus 862 kilojoules per mole. And that gives us this answer here. And the negative sign here tells us that this is in fact an exothermic reaction. The minus sign is in relation to the reactant molecules. There is a negative change in energy for the reactant molecules. Therefore, the energy has been transferred to the surroundings. So whenever you see a negative sign in a bond energy, that means it's exothermic. Okay? If it's a positive sign, well, that must mean it's endothermic. Okay? So this question here, it is an exothermic reaction. So the next stage is reaction profiles. And what a reaction profile is the following. So a reaction profile displays the relative energies of the reactants and the products over the course of a chemical reaction. So let's look at the following. So this is a reaction profile for an exothermic reaction. So the y-axis is the energy of the reactants, okay? And the x-axis is time. So time is increasing, and this is the energy, how the energy changes of the reactants and the products, okay? So initially for an exothermic reaction, the reactants have this level of energy, okay? And then at the end of it, they have a reduced level of energy. And this is because there has been a transfer of energy from the reactant to the surroundings. So that's why we see a decrease in the level of energy. But we also need to notice that there is this gap here. So initially, as the reaction goes on, the energy of the reactants increases. And that's because to initiate the reaction, we need to break the bonds. And breaking bonds is an endothermic process. It requires energy. So we get this blip called the activation energy. Activation energy of the chemical reaction. And this is the energy just to kickstart the reaction, break the bonds so they can then form new ones. But the overall net change here means it's an exothermic reaction. And this is the measurement you have to make to calculate what you would work out from your bond energy calculation, not the distance between here. That's different, okay? Now let's look at from an endothermic reaction. So an endothermic reaction has the same scales, so energy on the y-axis and time on the x-axis. And what we'll notice here is that the reactant have less energy than the product molecules. So there's been a transfer of energy from the reactants to the products. And likewise, if you're doing your calculation of the change in energy, you calculate the distance between the reactants and the products, but you don't calculate this distance as well. As before, this is the activation energy gap for that reaction. So cells and batteries. So chemical reactions in a cell or a battery occur and then they produce electricity. Okay? And the layout of a cell, because not just any chemical reaction will produce electricity, you need to have it set up in the following. So what we have here is we have 2 electrodes in a solution with a wire connection to complete the circuit, and then a potential difference is recorded here. Okay? Now, in order to record a potential difference, you can't just use any materials as the electrodes in the solution. They need to be specific things. And the first requirement is that you need 2 electrodes which are metals of differing reactivity. Metals because they need to conduct electricity, and they need to be different reactivity, and we'll go into that in a little bit. So the next bit is this solution here needs to be an electrolyte solution, which is a liquid that contains ions that react with the electrodes. Okay, so we need to have a solution, an electrolyte solution, that is both contains ions, but those ions also react with the metals in question that are the electrodes. Okay, so those are the conditions, and make sure you're familiar with that. But the final thing we also need to do is that we need to have a wire connection, because these reactions will occur, but they're not going to create an electrical circuit which can then be used to capture electricity if there's not a connection. So that's what these wires satisfy that issue. Okay, and the size of the potential difference depends on these factors. So obviously the electrolyte, because different metals react differently, leading to a charge difference if that changes, but also the difference in reactivity of the metal electrodes. So you'll be familiar from the reactivity series that we have a series of metals of differing reactivity. Okay, and if the difference in metals is greater in reactivity, then the potential difference will therefore be greater. Whereas if we have a smaller difference between the reactivity of the metals, the potential difference will be less, will be a lower potential difference. Okay. The final thing on this slide is that we need to know the definition of a battery and how that differs to a cell. So here we go. A battery is a collection of cells connected in series. So the final part of this lesson is fuel cells. So what is a fuel cell? Well, a fuel cell is an electrical cell that oxidizes both oxygen and hydrogen. Okay? So what happens? Well, we have two parts to it. We have a negative electrode, which is this electrode here. And hydrogen enters in this here and undergoes this reaction, which is an oxidation reaction because it is losing electrons to form H+ ions. Redox, remember. And then at the positive electrode, this is the reaction that occurs. Okay, and if you're doing HIAT here, make sure to be familiar with these equations because that will be very helpful for your exam. Now these are the two half equations that occur, and if we put them two together, we'll get an overall reaction, and this is the overall reaction that's going on here. Hydrogen and oxygen react together to form water. Now this is a fuel cell, and this produces electricity, and this is a very green way of producing electricity because the only waste product is water, which is a green product. And also, fuel cells don't produce any toxic waste, which we just discussed, but also if you're disposing them, well, batteries are highly toxic to dispose of, which are still using electricity, so not fossil fuels, but they're highly toxic to dispose of. But fuel cells don't produce any toxic waste, so that's a big advantage, and we do need to be aware of the advantages and disadvantages of a fuel cell. Okay.